Good morning. My name is Jared Ziegler, and my teammates here are Rick, Chris, and Kevin. This is Team 54 Compact Radar Team for ECE49022, and here is our final demo for the semester. Our team mission was focused on designing a compact radar that could be mounted onto a drone to perform obstacle detection and SAR imaging. The primary requirements for that radar are it can be drone mounted, can detect objects in a 360-degree field of view, sweeping every 2 seconds. The radar will have its own power independent of the drone, and its application will be lightweight, and the radar will also detect a range up to 100 meters, detect speed with Doppler shift, and perform SAR imaging. Pictured here is our full block diagram color-coded by subsystem. The microcontroller here and the power subsystem are at the core of the design, both in charge of driving and controlling the antenna motor, antenna driver, transmitter, and receiver subsystems respectively. The signal processing of our design would be done remotely, given transmitted radar data sent from the microcontroller over SPI communication with the Bluetooth subsystem. To start things off, we have Rick to go over the mounting and rotation of the full design, and each subsystem's owner to present their respective demos following after.
Here is the assembled system. As you can see, it can spin 360 degrees. This would be powered by the motor if the PCB did not have a fault, and it would be mounted to the drone from those screws right there and rotate about that axis, and thus would sweep a full 360 degrees if the radar was functioning. And we weighed the radar to determine whether it met our lightweight requirement, and it came in at almost half the requirement. So that is successful.
The power subsystem consists of a battery, 3 voltage regulators, and a low battery detect circuit. Unfortunately, the onboard power system cannot be properly demonstrated due to a hardware error that shorts the 5V and 3.3V power rails to ground on the radar PCB. However, the design of the regulator circuits was validated on a breadboard circuit for the midterm demo, and a simulation was used to validate the design of the low battery detector, which generates a low battery GPIO signal to the microcontroller when the voltage approaches the 11.1V minimum.
Here are the requirements demonstrated with the transmitter and receiver subsystem. This is the phase locked loop simulation of the transmitter subsystem done in ADI Sim PLL, and here are the results. This is the code flow of the ADI4158 frequency synthesizer chip in the transmitter subsystem that is programmed to output a sawtooth waveform with a center frequency of 5.8 GHz with a frequency modulation of 75 kHz based on the datasheet. And this code flow shows which values should be assigned to which registers. This is the receiver RF chain simulation done in ADI Sim RF, and the results are shown down here. This is the LT-SPICE circuit simulation of the baseband filter in the receiver subsystem, and this is the result of the frequency response showing the negative 40 decibel per decade roll-off below 25 kHz, and here's the transient analysis.
As previously demonstrated in the midterm demo and seen here, the ADC and GPIO functionality for the Nucleo board was successfully implemented, its code being ported over to the new STM32 project files for our higher spec onboard microcontroller. The ease of public sharing and version control for programming was streamlined using GitHub, and code dedicated for the integrated functionality of the radar system was developed from there. The block diagram for the MCU shown here was updated to accommodate the desired serial wire debug method of programming through the Nucleo board's built-in ST-Link. However, due to hardware ground faults in the PCB design and assembly, the onboard microcontroller was unable to be programmed, and only its desired functionality can be shown here. The main.c's primary functions would be to initialize the ADC with DMA and SPI to Bluetooth module peripherals. They're built-in HAL library functions allowing them to run while the motor controller portion of the MCU works within the while one loop, and interrupting said loop with SPI and ADC callbacks whenever the DMA buffer would fill up to 2048 bytes. These callbacks would indicate a full sweep of about 2 seconds according to our system requirements, and would transfer the gathered 2048 ADC samples as well as the current motor position and battery status of the system before returning to its regular operation in the while one loop.
This is the final demonstration for the signal processing subsystem. It will be demonstrated on its own to show that there is a functioning system for interpreting and displaying data in real time. In addition to the two UI elements visible on the right, the debug windows on the left are shown for demonstration purposes to indicate communication between the MCU and computer. Bluetooth pairing is automatic as soon as both Bluetooth devices power up. Data streaming begins with the push of a button and occurs non-stop in the background. Communication is two ways, and commands can be sent to the MCU at any time. Due to limitations of the Bluetooth hardware available, data transfer is extremely slow, so the footage is accelerated. The source of the signal is the Nucleo F413ZH, which stands in for our MCU. It is generating white noise and sending it to the Bluetooth Low Energy client, which wirelessly transmits it in small packets to the Bluetooth Low Energy server connected to the PC. The direct USB connection is not implemented in this demo. Here, it can be seen that the UI addresses requirements for displaying data to the user. While this demo was running, I manually collected 25 SAR samples to display as one image. This image is shown here. To ensure the outputs match what would be expected by the user, I used MATLAB to generate a sine wave signal with a sinusoidally modulated frequency and white noise added in, and then processed this signal to create these images. The signal-to-noise ratio is 1 to simulate worst-case conditions. After modifying the UI to read this signal from a file, it generated these results, illustrating the system's ability to decode useful information from input data.